Have you ever just stopped and really thought about what sound is? I mean, really. Today, we're going to follow the incredible journey of a single sound, from the very second it's created all the way to the instant you hear it. It's a story that's happening all around us, all the time.
Now, here's a wild idea for you. Think about a car horn, a violin, your own voice. They all sound completely different, right? But what if I told you they all share the exact same origin story? The same fundamental spark?
So let's do it. Let's pull back the curtain and uncover that one single secret ingredient, the one thing that is absolutely essential for any sound to even exist. And the secret is vibration. Yep, that's it. Every single sound in the universe begins with this simple, rapid back and forth motion. Your vocal cords when you speak, a guitar string when you pluck it, a ringing bell, they're all vibrating. And that right there, that's the birth of sound.
Okay, so we've got a vibration, a simple little shake. But how in the world does that turn into something that can actually travel across a room and into your ears? How is sound actually born from this?
This is such a cool way to see something that's normally invisible. I mean, you can't see the air vibrating when you hit a tuning fork, but dip that same vibrating fork in water and bam, you see the effect of that energy immediately. Those ripples, those splashes, they show us exactly how the fork is pushing everything around it, creating a disturbance. And that disturbance, that's the beginning of a sound wave.
All right, so our disturbance has been created. It's leaving the tuning fork or the speaker or whatever made it. Now it starts its great journey to our ears. But how does it actually travel? Well, here's the thing. Unlike light, sound can't travel through the emptiness of space. It's not a solo traveler. It needs a ride. It needs something to carry its energy. And that substance is called a medium. That could be a gas, like the air we're breathing, a liquid, like water, or even a solid, like a wall. Now, this is a super common misconception, so let's clear it up. When I talk, the actual air particles from my mouth don't fly across the room into your ear. No way. Instead, think of a slinky. Each little ring just wiggles back and forth, bumping into its neighbor and passing the energy along. It's the wave that travels, not the particles themselves. They pretty much stay put.
And this type of wave has a name. It's called a longitudinal wave. As the sound source vibrates forward, it squishes the air particles together into a high-pressure zone. That's called a compression. Then, as it moves back, it leaves a little low-pressure gap, and that's a rarefaction. So a sound wave is really just this repeating pattern of squish and stretch, compression and rarefaction, moving through the air.
And you know, what that sound travels through makes a huge difference in its speed. I mean, look at these numbers. In air, it's about 346 meters per second. Fast, right? But in water, where the particles are way closer together, it's more than 4 times faster. And then you get to solid steel, and it's an absolutely staggering 17 times faster. This is exactly why you can hear a train coming by putting your ear to the rail long before you can hear it through the air. Steel is like a superhighway for sound.
So, if all sounds are just these waves of vibrations, what makes a high-pitched violin note so different from a low-pitched drum beat? Well, we're about to decode the 2 key characteristics that give every single sound its unique identity.
First up, we have amplitude. Now, the easiest way to think of this is just the size or the intensity of the wave. The bigger the vibration that starts the sound, the bigger the amplitude of the wave. And for our ears, amplitude translates directly into one thing: loudness.
This is super intuitive. If you tap a drum lightly, you create a small vibration, right? That means low amplitude, which results in a soft sound. But if you hit that same drum with a lot of force, you create a huge vibration with high amplitude and a loud sound. It's that simple. More force equals more amplitude, which equals more volume.
The second identifier is frequency. Now, this isn't about the size of the wave, but its speed. Frequency measures how many of those complete back and forth vibrations happen in just 1 second. And the unit we use for this is hertz. Now, our brains don't really process the world in hertz. That's a bit too technical. We have a much more musical and intuitive way of understanding frequency. We perceive it as pitch. And the relationship is totally direct. A sound source vibrating slowly, like a big cello string, produces a low frequency, and we hear a low pitch. A source vibrating very quickly, like a flute, produces a high frequency, and we hear a high pitch. So there you have it. Loudness is all about amplitude, and pitch is all about frequency.
Okay, we've seen how a sound is born and how it travels, but the journey isn't always a straight line from A to B. What happens when that wave hits a wall, a mountain, or any other obstacle in its path?
Well, just like a rubber ball bouncing off a wall, sound waves reflect off surfaces. They actually obey the same physical laws as light, which means the angle they come in at is the same angle they bounce off at. And when that reflected sound travels all the way back to your ear and you hear it as a distinct, separate copy of the original sound, that's what we call an echo.
So why don't we hear echoes all the time? Well, it comes down to our brains. Our brain actually holds on to a sound for about 1/10 of a second. If a reflection gets back to us any faster than that, our brain just merges it with the original sound. So to hear a distinct, separate echo, that reflection needs a delay of at least 0.1 seconds.
And we can actually turn that time into a distance. Since sound travels at about 344 meters per second, it needs to cover about 34.4 meters in that 0.1 second window. But remember, that's the round trip to the surface and back again. So the surface itself has to be at least half that distance away, 17.2 meters. Any closer and you just won't hear a distinct echo.
So what happens in a big hall where the walls are closer than that? You get thousands of reflections all arriving in under 0.1 seconds. They all just merge into a single lingering sound. This persistence, created by countless blended reflections, is what we call reverberation.
So from a simple shake, a wave of energy is born. It travels through the world, defined by its loudness and its pitch, until it reaches our ears, sometimes after bouncing off a few surfaces first. Every single sound you hear has completed this incredible journey. The world truly is a constant symphony of vibrations. And that brings us to the end of our journey. So, the next time you step outside, I want you to listen a little differently. Now that you know the whole story of sound, what will you listen for? The amplitude of a passing bus? The frequency of a bird's call? Maybe even the faint echo off a building down the street? Thanks for listening.